Problem 17 is another good example for pure translational motion. In this problem, we have this uniform log, which is connected to the roof with these two cables. And we know all the geometry. And it is in a stationary condition, and suddenly we are releasing it. And the question is, immediately after releasing it, what's going to be the tension in these two cables? Immediately after releasing means the velocity is still zero. If I release this, it's gonna go down like this, right? But at the beginning, right after releasing, there is no velocity. So you should keep that in mind. And the question is, what are the tension in these two cables? So before trying to solve this, just you should notice that the direction of this log is not going to change, right? Because we have a parallelogram here. These two cables, the log and also the roof, they all making a parallelogram. So this log is going to be always parallel to the roof, parallel to this line. So always we are going to have pure translational motion. So in this problem 2, alpha is going to be equal to 0. There is no rotation for this log. I would suggest to think about this problem for 15 minutes at least, then see the rest of the video. So if I want to draw the free body diagram of the log, first of all, I have gravitational force, mg, which is given 60 pounds. I also have tension in this cable, let's call it TA, and tension in this one, TB. And the other thing that we need to define in our free body diagram is the coordinate that we are going to use. If you think carefully about this, you're going to see all the points. For example, point A. If it's moving, if you track it when it's moving, A is moving on the circle about this point, right? Because it is connected to the top with that cable. Same thing for B. B is moving on a circle with the center. And same goes for the centroid. The centroid is rotating about this center, right? So it might be better to use normal tangential coordinate. Tangential is going to be perpendicular to these cables, and normal is parallel to the cables. Tangential shows the direction of the movement for the centroid, and n is perpendicular to the path of movement. So I'm going to use this tangential normal coordinate. You are going to see it's going to be very useful. Now, what equations do we have here? Sum of the forces in tangential direction is equal to mass times acceleration in the tangential direction. In the normal direction, same thing. Sum of the moments about the centroid is going to be equal to 0 because alpha is equal to 0. So I alpha is 0. So let's start with that one. Sum of the moments about the centroid is equal to 0. Moment of mg is 0. It is passing through the centroid. Moment of TA is going to be clockwise, so it's going to be negative, and the value of it is going to be 2 feet times force times sine of the angle between them, right? That's the way you'll find the moment. So I'm going to have negative TA times 2 times sine of 60. Moment of TB is going to be this distance. Oh, I made a mistake. 2 is from here to here. The length of the log is 3 feet. So from here to here is going to be 1.5. So I have to correct this. And from here to here is going to be 0.5. So moment of TB is going to be 0.5 times TB times sine of the angle between them, which is 60. Or you can say sine of 120. They are the same. Sine of 120 and sine of 60 is the same. And the direction of the moment is going to be counterclockwise, so it is positive. So plus TB times sine of 60 times 0.5 is equal to 0. So these signs are going to cancel out, and if you simplify it, we are going to see TB is equal to 3 times TA. So we got one equation for the tensions. I need another equation between them to find them. Sum of the moments, sum of the forces in the normal direction is going to be equal to mass times acceleration in the normal direction. And again, to remind you, acceleration in the normal direction is equal to velocity squared divided by rho, radius of curvature. So if I know the velocity of the centroid, the radius of curvature of it is going to be the length of these cables, because the distance from here to here is the same as the length of the cables, and centroid is moving on a circle with this center. So rho is going to be this. However, velocity at this moment is equal to 0 because we just released it. Right. So velocity is equal to 0. Acceleration in the normal direction is going to be equal to 0 too. So the forces that we have in the normal direction, TA and TB, they are both in the normal direction. And mg has a component in the normal direction. That's the positive direction for normal. The component of mg in that direction is gonna be negative. It's gonna be mg times cosine of this angle, which is 30. So minus mg times cosine of 30 is equal to 0. So we got our second equation to find TA and TB, 1 and 2. So if you combine 1 and 2, you're going to be able to find both of these forces. So if you solve this 1 and 2 equations, you're going to see TA is equal to 12.99 pounds, and TB is equal to 39 pounds. The question is asking about something else as well. We need to find the tension and also angular acceleration of the cables. So angular acceleration of the log is 0, but it doesn't say anything about angular acceleration of the cables. The cables are rotating, right? I'm gonna call angular acceleration of them as alpha c. How can I find that? If you look at our solution carefully, we used this equation and this one, but I didn't use sum of the forces in the tangential direction. Sum of the forces in the tangential direction is equal to mass times acceleration of the centroid in the tangential direction, right? And the forces that we have in the tangential direction, TA and TB, both of them are perpendicular to tangential direction, so they don't have any component here. The only force that we have in the tangential direction is going to be mg times sine of 30. That's the only component that we have in the tangential direction. So I'm going to have mg sine of 30 is equal to m times acceleration in the tangential direction. And g is equal to 32.2. And m is going to cancel out. So acceleration in the tangential direction is going to be 16.1 foot per second square. But why did I find this tangential acceleration? As I explained, this log is just moving purely translational. It means acceleration of all the points on this log, they're going to be the same. Same thing for velocity of them. Acceleration of A, centroid, B, this point, all of them, they are moving similar to each other. They have same velocities and same accelerations. So acceleration of this point is going to be the same. So acceleration of B is going to be just in the tangential direction, AT. And because B is a point on this cable as well, Acceleration of B in tangential direction is going to be length of the cable times alpha of it, right? You know it from previous chapter. So acceleration in the tangential direction is going to be that length, which is 2, times alpha of the cable. From here, you're going to be able to find acceleration, angular acceleration of the cable, which is going to be equal to 8.05 radian per second square.